Thank you very much, Jonas. Well, it's a great pleasure to have the opportunity to talk about some of the things of our activities. Just before starting, our group is a pretty big group working on different things, as you see here, on locomotion, on prosthetics, inspection, actuators, and different things. But what I want to address today are two specific projects, and especially addressing how we do address projects from a practical point of view, sometimes starting from a theoretical point of view. So from a practical point of view, we have a big lab and rapid prototyping facilities, and we really try to build things. On the other hand, many ideas start from conceptual design. So, for example, from the theoretical side, what we are active is for what I call port-based robotics, which stems actually from ideas from bone grafts and port Hamiltonian system theory. And also the geometry is a major line that we always use in our research. So things we're using, for example, Lie group, screw theory, and these kind of things, and nonlinear modeling and control. So looking at this, I want to talk about two projects that actually have stemmed from these two directions. So the first one I will want to talk about is Robert. And as you can see here, the focus is really on biomimetics. So we started from a practical biomimetic point of view. And the status of that project is that we have a spin-off that really is looking into the market. I will come into that into the moment. So we started from a practical point of view, went to a theoretical point of view. And the other one, which is the fast-running energy-efficient quadruped, is actually starting completely the opposite way. So the idea there is really to do something extremely energetically efficient, and we are starting from a conceptual design, so we go from theory to practice. But let me start first to talk about the robots. So the robots is something we have a spin-off that you see here, ClearFly solution, and actually I was very pleased just to get a few hours ago to see this. So I was tweeted that we were on CNN Tech with this project, so I was extremely happy about it. So I have the opportunity to talk about it here right now. So let me say a few things about bird strikes. So if you look only at the aviation setting, well, there is an increase in bird population due to bird reservation programs, especially, I don't know, here in the US, but in the Netherlands, the number of geese are increasing a lot due to the fact, the natural preservation program create that. On the other hand, birds are great animals, but the damage that they give to normal aviation is huge. So the financial damage has been estimated between $3 billion and $4 billion, and only the airport of the Amsterdam and Schiphol is investing $2.5 million euros a year, which is more than dollars, for prevention, because it can be very dangerous, as you can see on the video on the down right. And also the agricultural issues, the damage to the agriculture industry is great. If we look at solutions that nowadays the airport use are, for example, bangers or lasers. So you see here some pictures of this stuff. But one of the funny things is that Nico, so the CEO of the company, a spin-off company, actually said that once he was went to the airport, and what actually saw with his own eyes is that the birds actually stay on these cannons. And when they pressurize the cannon, they recognize the click of the valve. They fly out, the bang bangs, and they come back. Okay, so they really learn this thing. And instead, predators are actually, they recognize the picture, very basically programming their brain that the motion of the wings is actually scare them and they fly away. So, so for this kind of application, like aviation and also waste management and agriculture, I think that robotic birds are really a solution. And this is a collaboration that we started, and I will show you our system, which we are still working on it. But first, let me give you some basics of flight. Well, I mean, really few ideas is that, an airplane basically flies because the wings create, it has a normal flight, due to the angle of attack, you have a lift and you have a drag. And the motors basically compensate for this drag and create acceleration, so that you can basically have enough speeds to create lift and stay in the air to compensate gravity. Well, flapping flight is different because not only with the wings you have to create lift, but you have also to create thrust to compensate from the drag. So basically in flapping flight what happens is, and you have a periodic motion. So what happens in flapping flight, basically, you have a continuous change of angle of attack. Basically, on the upstroke, you try to minimize the drag, and then when you go to the downstroke, you try to create thrust, and you increase a little bit the angle of attack with respect to the flow of the air, which is a sinusoid due to the motion of the wings up and down. Furthermore, what is very important, and we realized, is that the flexibility of the wing, if you want to create robotic birds, it's really essential. So if you make very stiff wings, it really would not fly. So as you can see here in this video, so you have those wings are the wings of our birds. If you notice, this is a very high-speed camera because the wing normally goes to 6 hertz, so they go pretty fast. And then you see that very clearly that during the downstroke, at the end of the downstroke, you have a twisting of the wings at the end. And that's due to, of course, the elasticity. And one of the crucial things about the design of the wings is really to make the material in such a way that this flexibility actually exists. Otherwise, it wouldn't fly. Well, let me tell you how this thing works. Well, the core of this bird is actually right here. So there is a mechanism inside the bird that actually let the wing flaps. And there is a 150 watt motor, and which, the mechanical efficiency is we try to increase it more and more. But usually what birds of that size, when they fly, they use in full flapping about 70, 80 watts. And our mechanical power we get for fly is 90 watts. What you see is indicated in the slide. You have those connection points where the wings are attached. And due to the certain count mechanisms, basically you create this phase shift during the upstroke and the downstroke so that you can have the change in angle of attack during the upstroke and the downstroke. And furthermore, it's not reported in the drawing, but you have an elastic element because you can imagine when you have the downstroke, you need a lot of power. So you have some elastic elements that basically help in storing the energy and doing the flapping flight when you go the stroke down. What you see here are some plots of real measurements. Are very small, but basically the frequency of flapping of the bird is about 5 to 6 hertz, and the body acceleration during the flapping are up to 3 Gs more or less. So you can imagine also that if you need to measure acceleration, there is a lot of disturbance in this effect. And in the future, would like to put vision on this thing, but of course you will have a lot of challenges due to the vibration you have there. And the throttle controls basically the frequency speed. And the role of the birds on the wings, there are little manifolds that basically can create the roll during the flapping. And the pitch is done with the tail. In the future, we want to actually do asymmetric fly, but we'll have to completely change the design of the actuator. Well, the electronic is actually all based on an Arduino pilot, and we have put some measurements on the wings so that the birds can actually change flight from flapping to gliding, as I'll show you later. And then also we have some airspeed sensor where we are trying to model the birds to get aerodynamics. One thing you can see here is that is now flapping, but there is now the control of the manifolds for stabilization. Autonomous stabilization is already working. So if you see when the bird is inclinated or pitched, that you will see the tail and the wing that are actually moving. So as I said, we work on this thing can work in flapping and in gliding, and the wings, of course, should be locked in the right moment, because, of course, you can imagine that if you would lock the wing like this, it would be unstable, right? So you need a certain configuration in order to be able to properly glide. And this is the bird. It really looks like a real bird. And the weight is about 730 grams, payload of 20 grams. And I think it's, as long as I know, and it's the only robotic birds that can go up to this speed at flying in this wind. I mean, there are very nice birds, like, the Festo bird is a fantastic design, but it can certainly not go outdoor with this kind of wind. And the wings is basically patented. The material is expandable propylene, and the shape and the way it is done is, and the flapping is patented. So here are some other cool pictures of the bird, and this is the top view of the wings. And actually we have also another bird, which is a much bigger bird, which is an eagle. And this is pretty impressive. What this flies is really huge. You know, it's a big thing. And more than 2 kilos and a payload of 150 grams. But before any further ado, let me show how this thing works. It's now gliding, and it can glide very well, and in a moment it will start flapping. It is also very important how to start flapping, because it needs a lot of power, so you actually need first to let the wings go up and then go down again. This is slow motion. And really, if you see it flying, I mean, you recognize the noise, but if you see it, you cannot distinguish it from a real bird. And it's very effective. We have the first tests, and it really, in waste management, when this bird is flying, a week after, there are no birds around. So it's really effective. So let me talk very briefly about this other conceptual thing. I will go much faster here, and if there is interest, I can say more separately. So this project is actually financed by the National Science Foundation. So you have a lot of great design of quadruped around here. So Boston Dynamic, Jonas' work at ETH, and there are other elastic locomotion machine like the one of me, IDA, also at ETH. But what we try to do, the thing that we want to do different than that is to really make something which is really extremely energetically efficient. And if you see in these designs, what you have very often, they are rocking very much, and then there is a big mass. So eventually you will have a lot of energy during contact where the impact takes place. A design which is different, and actually we've been collaborating with, the one of Sang-Bae Kim at MIT. The first design of is Cheetah. He has an elastic spine. That was actually the inspiration to do what we want to do now. And actually in the second design, I talked to Sang-Bae, he's actually got rid of the spine, but he still believes that that's actually the way to go. And what we want to do is really looking at the biomimetic, but mainly in intrinsically dynamics, in which you can create most of the torque with reversible energy storages of springs in the spine and in the legs. In order to do that, you need a tool which basically allows you to analyze these energy transfers very well, which are Porter-Hamiltonian system. So as I said, the goals are basically to make very soft feet so that you have diminished the energy losses, which is intrinsically there due to impact, and you try to create a geometrical spine and some oscillations that can resonate on the front and the back side. So what you see here on the left is a video of a puma, and what you see down is actually some video graphing that we've been working on, and down left you see a video which analyzes the motion of the front and the back of the puma, and what you see down right is the first simulation of something which is completely passive. So you actually, just by geometrically design the spine, you can create oscillation and the things can walk forward. But I will actually talk about what is on right, so synchronization. So in 2004, we worked on something which some other people actually called the energy router. And this idea actually has brought some insight in many different things. So basically it's a way to steer energy flows in dynamical systems. And it has been used, what was basic to use, for example, tanks in telemanipulations, energy continuous tracking of nonlinear system, some actuator, novel actuator design, and van der Pol oscillators, power continuous van der Pol oscillator, I will talk about it briefly, and other issues. And by using this power distribution, we actually want to tackle this problem on the Cheetah from a conceptual point of view. So if you look here, for example, if you have two oscillators, harmonic oscillators with variable impedance actuators, the idea is that you basically want to synchronize these two oscillations by changing the stiffness. And you want to change the stiffness by actually transferring energy from one stiffness port to the other stiffness port. Let me tell you more about it. So if you see here on the right, you can consider the storage of elastic energy as a function of the displacement and the stiffness itself. So the dual variable of the change of stiffness, k dot, then will be the partial derivative of the energy with respect to k. And therefore that you create a kind of port which you can then use to transfer energy from one side to the other. So if you see the last two equations on the bottom, basically if you implement this for any value of R, you will have a closed energetical consistent system. So you will not create energy, you will not dissipate energy. And therefore by doing that, what you could see that by measuring the phases as indicated here, so you basically measure the phase, you give a desired difference in phase, and we're a simple controller which steers this, what is called, this is a bond graph notation, is basically this R value. What you can see is that this actually is very effective and you achieve exactly what you want. So you see that the 2Ks after a while stabilize, and yet you see that you reach the phase change that you wanted to have. If you look at the energy levels, what you see is that the total energy is constant because everything is done completely energy costless. And then you see that the two energy of the two springs, of course, they change, and eventually they stabilize to certain values together. Without going into details, and here you can also basically, what this indicates is actually parallel forces around the springs, because of course every time in practice you hit, you lose energy due to impact. So you will need also some control of to inject energy to keep these oscillations. So what you can do is basically doing the control of the phase by this method, by changing the stiffness, and by some parallel actuation on the springs, you can inject the energy. And this turns out to work well and to basically give the phase shift you want to have, the amplitude you want to have, and in this simple situation it works. Of course, in practice, you have a hybrid situation in which you have contact and no contact. So you can only apply force if you are in contact, because then you can really push on the ground. And it turns out that that can be easily extended to that as well. And if you go to limit cycles, then what you see here is a little setup you are building to test this idea. What you basically can see is that, as we showed in the past, that you can actually create energy continuous oscillation based on Van der Pol oscillators. Instead of storing, what you see here is actually a phase space of the Van der Pol oscillator with a dynamic extension. And if that dynamic extension, you couple it to another oscillator, you basically can transfer energy from one oscillator to the other. So what you see here is, for example, the synchronization of two Van der Pol oscillators. And what you see here on the left is one, the other one is on the right, and the notation is different for the way you implement a Van der Pol oscillator. That's not important. And basically what the controller does is shifts energy from one side to the other and is able to synchronize these two Van der Pol oscillators. The last step will be, of course, to generalize this and to any limit cycle you want to have. And this is something we are actually working right now. We'll send it to ICRA for next year. What you see is basically if you have any two dynamical systems, and you have two controllers that create limit cycles in two dynamical systems, then actually what you can then do is to generalize this, and you create limit cycles. And basically the idea eventually will be that if you have this quadruped, you will have a front side and a back side, and you define a certain motion of oscillation you'd like to have, and you would like to try to get this oscillation as much as possible with the resonance of some elastic and kinetic, potentially kinetic energy with resonance. And of course, injecting the energy to compensate for dissipation you cannot do anything about. And then to transfer this energy via the spine. That's basically the idea. And we are looking at mechanisms also that can actually implement these theoretical concepts in a practical sense. So this brings me to my conclusions. So I show you some novel system that stand for practical theoretical approach. You see that you can approach the novel system either from one side to the other. I think that the power is actually to do both. And port-based robotic has already shown some to be useful. And I think that this idea, I'm very excited about this way of looking at a cheetah by this insight from a system theoretic point of view. And I think that it will have really the potential to achieve much more energy efficient systems. So the future work, we will complete the GPS for the bird, the navigation, and we'll work at soaring to scavenge energy from the wind. And with Freak, of course, we'll try to build this spine. Thank you very much for your attention.
Hello everyone, my name is Minjun Kim from Postech in Korea. This presentation is about control of flexible joint robots using DOB, which will be applied to the motor side dynamics. So recently, various types of mechanisms are developed and implemented in robotics. In particular, utilizing flexibility in robot joints became one of the important research topics. And naturally, control of flexible joint robots became an important issue. Using joint torque information, we can fully utilize the characteristics of the flexible joint robots. The goal of this research is to eliminate such uncertainties in the motor side using DOB. Flexible joint robot dynamics basically consists of two parts. One is motor side dynamics, which is linear, and the other one is link side dynamics, which is nonlinear. And joint torque is the torque acting between them. And I would like to point out that the most of uncertainties exist in the motor side. So therefore, in this study, I want to eliminate this uncertainty by applying DOB to the motor side. It seems possible because every external torque applied on the motor inertia is known, and the dynamics of motor inertia, dynamics of motor side is linear. This is block representation of flexible joint robots. The DOB will be applied only to the motor side, which is coupled with link side. Therefore, the stability of the overall system should be discussed more thoroughly. And the key finding of this study is actually very, very simple. To guarantee the stability, the estimated signal should be fed back into the controller, not measured signal. Actually, typical implementation of DOB takes measured signal feedback. And I will omit every technical details in this presentation, but instead I will show you one video. This is one of my experiments. Ideally, if there is no friction at all, the joint should behave like a free joint. However, it suffers from high frictions. This inertial reshaping is another technique that can deal with joint frictions very simply, but still it does not behave like a free joint. When DOB is applied as proposed, it moves like a free joint, as you can see. And okay, this is it, and thank you for listening. I look forward to see you in the interactive session.
Good afternoon, everyone. My name is Moussa Benoir. I am a robotics PhD candidate at l'IEM in Montpellier, France, and I'm here today to talk to you about the work that I have done with my supervisor regarding the control of redundantly activated parallel kinematic manipulators. So, parallel kinematic manipulators are known for their great performance compared to the serial ones. However, these advantages never come without drawbacks. Indeed, controlling such a mechanism is a challenging task due to the inherent complex nonlinearities. Consequently, to design an efficient control strategy, the nonlinearities of the system and eventual disturbances have to be taken into account. For this reason, researchers are always looking for new sophisticated control schemes to deal with such constraints. So recently, a new feedback control strategy called the robust integral of the sign of the error, or simply RSJ, has been introduced. This control technique can accommodate for a large class of smooth bounded disturbances, satisfying some non-restrictive assumptions about the system. The control action of RSJ features a unique signal function and guarantees a semi-global stability result. The region of attraction of the controller can be made arbitrarily large by increasing the control gain Ks. While the RSJ action is enough to ensure asymptotic tracking of the desired trajectories, it is, however, beneficial for us to take advantage of the knowledge of the system to improve the performance of the closed-loop system. For this reason, we propose herein to augment the RSJ control action by a model-based adaptive feed-forward term, as you see in the current slide. Moreover, to deal with the redundancy constraints, we propose to project the computed control inputs using the kinematics of the manipulator to get rid of the internal efforts that only appear in the case of redundantly actuated parallel kinematic manipulators. The proposed controller is illustrated on the current slide. To validate this controller, we propose to implement it on a parallel kinematic manipulator redundantly actuated PKM available in our lab, namely the GLV. So we implemented this controller and we experimented two scenarios, a nominal scenario and a payload handling scenario. And in both cases, we see that the proposed extended RISE controller performs better, much more better than the original RISE controller. That's it for me. Thank you for your attention, and I'm looking forward to see you in the interactive session.
Good afternoon, everyone. My name is Rana Soltani, and today I'm going to present you the work I have done under supervision of my advisor, Dr. Suhada Jayasuriya at Drexel University, on the problem of dynamic modeling and path planning of mobile robots under realistic constraints such as sleep and actuator limitations. So the purpose of the research was to develop a comprehensive dynamical model for two-wheeled mobile robot subject to constraints such as sleep and heart control constraints. For this purpose, we have developed a novel sleep model for both longitudinal and lateral directions. The current models in the literature for sleep are either too complicated, which adds to the inherited complication of the dynamical models of wheeled robots, or they are too simple, which cannot capture the accuracy and details of the sleep model in both longitudinal and lateral directions. The advantage of the proposed model is that it is accurate, though simple, and also it is computationally efficient. We have done experiments, some of which are shown here, and to verify the accuracy of the proposed model, we have done simulations using the proposed model and some of the models current in literature, and the comparison of the simulation results with the experimental results show that our proposed model is accurate enough and captures the details both qualitatively and quantitatively. Also, we have done analysis on the feasible directions of movement for the mobile robots. And these analyses show that the direction of movement of robot is affected by velocity and heading of the robot. We call these directions constraint directions, and the insights gained through this analysis actually inspired us in developing a new path planning algorithm, which is actually a finite dimensional search procedure which eliminates having to deal with 2-point boundary value problems resulting from classical optimal control formulations. We have done some simulation results using this path planning algorithm, which shows that the robot is able to move toward the desired trajectory. I will be happy to discuss this research more in the upcoming interactive session, and thank you for your time.
Hi, I am Professor Cheolgu Kang from Kongung University in Korea. This is the work done with my student about driving a closed-form solution for extra-insensitive EIM shaper. The motion control of flexible arm is composed in general of rigid motion and flexible motion control. Input shaping control is to suppress residual vibrations of flexible motion. The objective of this paper is to obtain a closed-form solution instead of numerical one for non-zero damping EI shaper. Input shaping is an open-loop control technique for reducing residual vibration by convolving a sequence of impulses with a desired command. The sequence of impulses are determined from given natural frequency and damping ratio of a flexible system. Conventional EI shaper is given by a closed-form solution for zero damping case and the numerical solution for non-zero damping case. as is shown here. So we try to find the closed form solution for non-zero damping case. We start with 7 nonlinear constraint equation with 7 unknowns. After extensive mathematical manipulations, we arrived at this partially analytical EI shaper, A1, A2, A3, in which pi is computed numerically using the bottom equation. For the 5% vibration tolerance, simulation result show that 2 EI shapers show a similar performance, but in general, analytical solution is preferred. To experimentally demonstrate, we developed an easy-to-use, reliable, compact, use-expandable, and cost-effective experimental apparatus, which can be driven vertically or horizontally using by rearrangement. Also, we developed a very convenient GUI in which you can change controllers and parameters easily and see the result quickly. Now I will show you a demonstration video. Without input shaper, there is a big residual vibration. But with the proposed EI shaper, we can remove residual vibration almost like this. If you have any question, let's discuss in the continuous session. Thank you.
Hello everyone, my name is Gino Lee. I'm postdoc in Italian Institute of Technology. I'm currently working with Nikos Sakarakis and Darwin Caldwell. Today I would like to talk about the terminal sliding mode-based force control for piezoelectric actuators. So first I would like to introduce our system, compact compliant actuator called compact. It has a passive compliance, so it can provide safe interaction, shock absorption, and also it has an variable physical damping, so it can remove undesirable oscillation from the passive compliance. So to provide physical damping regulation ability, we use some piezoelectric actuators, which creates some friction forces into the system. So to emulate the desired damping behavior, we definitely need a precise and robust force tracking controller for the piezoelectric actuators. So the system can be modeled as a mass spring damper system, but the problem is it also contains a highly nonlinear dynamics, such as an hysteresis, and also it has a creep effect, causing the high overshoot responses. So our control approach is to have dynamic compensation, which is model-free, and we insert desired dynamics, which is fast and accurate. For the dynamic compensation, just imagine we have an unknown dynamics, and if we know input-output values, then we can estimate the values from the unknown system. So in our case, we have a control input and measure the force, and we always have a time delay between those two because of the causality. So we call this system force-based time delay estimation. And for the desired dynamics insertion, we design an integral type terminal sliding mode manifold. And also we designed the dynamic attractor using fractional terminal sliding mode. So this is some new type of terminal sliding mode. And also the terminal sliding mode provides an accuracy and robustness into the system. And the dynamic compensation is model-free, and it's very easy to implement. Just a couple of lines of the code. So in our experimental result, we confirmed the hysteresis effect and the creep effect was nicely compensated. And also the controller provides them very fast conversions. So for the sinusoidal comment, the control bandwidth is almost close to the system bandwidth. Please come to my booth and see more details about my paper. Thank you very much.
Good afternoon, ladies and gentlemen. My name is Luis Cañete, and I'll be presenting the development of a single controller for the compensation of several types of disturbances during task execution of a wheeled inverted pendulum assistant robot. So in our laboratory, we are developing an inverted pendulum type assistant robot. The key word here is assistant robot. So there would be situations where the robot would be working in close proximity with humans. So one requirement for these types of systems would be that the manipulators of the system be safer than other types of manipulators. So one solution that we are proposing is the use of lightweight and low torque manipulators. So this would make the arms of the system inherently safe, but it would also make the inverted pendulum assistant robot sort of ineffective. So to solve this problem, we are relying on the inverted pendulum key feature of the system. So using its own weight and its own balance, the system basically just balances out whatever large torque that is required during task execution. So with this, we think that we have a good balance between safety and the workability of the system, since we can still apply a large torque when required just by using the post and this weight of the system. So controlling the eye pentar it always starts with balancing control. But we are not just trying to balance an inverted pendulum system, we're actually trying to make it do stuff like load lifting, ramp traversal, step climbing, and all these other tasks. Now the problem is that these tasks introduce changes into the system, model inaccuracies, maybe unknown dynamics. So instead, so to control the system, this would typically require us to have several controllers, one for every single type of task. Instead, we can actually assume that these tasks introduce disturbances into the system so that every single task will then become a disturbance, reducing the control to a balancing control system plus a disturbance compensation method. So using this, we are able to create a one controller, many tasks idea that we are trying to pursue. So as you can see here, we have been doing this for quite a while now, and we have been successful in performing all these tasks that the system is required to perform. What happens is when the system is required to do something, something changes in the system, and these changes are estimated by the extended state observer right here. The changes are then compensated, reducing the effects of these disturbances. So to create a new task, we just need to change the trajectory of the system. So I would really like to talk to you about our research in great detail with all these key points. So please come to the interactive session later. Thank you very much.
Good afternoon. I am Fabrizio Flacco from the University of Rome La Sapienza. I'm talking about a reverse priority approach to multitask control over the redundant robots. So we are talking about the inversion of the differential kinematic of a robot. We have multiple tasks with priority, so we have a different multiple velocity for different points of the robot, and we want to compute the joint velocity or acceleration or torque, it depends on your tasks, to accomplish these tasks. As you probably know, you have the problem with the kinematic and algorithm singularities that may affect the correct hierarchy of your tasks. So the classical solutions are to use damped state inversion or to relax low priority tasks. So to understand, we just take three scenarios. The first scenario is with linear independent tasks, so tasks that can be accomplished in the same time. And the second scenario with three linear independent tasks with a singular task. And the third scenario with linearly dependent tasks, so three tasks that cannot be accomplished in the same time. So the classical way is to compute the solution for the highest priority task and then to compute the lower priority task by projecting in the null space of the higher priority tasks. But you can have some problem. In the first scenario, you don't have any problem, so you get all three tasks. In the second scenario, when you have the singular task, you have to use a damped state inversion, so you are deforming the primary task, even if it was feasible. Also, when you have linear dependencies, so you have the so-called algorithm singularities, and also in this case, you have to use a damped state inversion, and you are deforming the tasks, especially the first task that was feasible. Our method is slightly different. So we start from the lowest priority task, and we go ahead by adding the other tasks by using a special projector that we proposed. So in the first scenario, you get exactly the same solution. In the secondary scenario, instead, since you compute the last, so the highest priority task at the end, you don't have the problem with singularity. And also when you have linear dependent task, you don't have this problem. You get exactly the highest priority task and the linear independent part for the second and the third task. So we propose some experiment with a quick evaluated robots. We show the performance of this methodology with respect to standard method, also with respect to the singularity robust method by Chiaverini. Besides this good characteristic, there are also many other possibilities with this approach, and you will see, if you're interested in this kind of problems, we will be happy to talk with you during the both interactive section. Thank you.
Ladies and gentlemen, in this video, you see the bionic handling assistant continuum robot developed by the German company Festo. Unlike common industrial manipulators, this robot has no rigid links and therefore can extend and bend continuously. The bionic handling assistant is a pneumatically actuated and flexible manipulator. I cannot tell you in this session how it actually works. If you're interested in that, come to the interactive session later. But what I can tell you is that this manipulator is inherently safe and therefore well suited for all tasks that require contact with humans. Now we want to build a dynamic model for this manipulator that is similar to the common models used for rigid links manipulators. Why do we want to do that? First, we want to be able to run real-time simulations, but we also want to create a model-based controller. So that's why we need a model that incorporates all the static and dynamic couplings between the sections, and it needs to be computationally fast and invertible. How can we do that? First, we select distinct mass points for each section, and then by choosing a well-suited kinematic model, the constant curvature approach, we are able to select rather simple section models and combine them serially. Using the Euler-Lagrange approach, we finally obtain the dynamic equations for each actuator. Of course, the calculations for m, c, n, and tau are not that simple and don't fit on this slide, but I can explain them to you later. And now I will tell you a little secret. Based on this dynamic model, we were able to implement feedback linearization on this whole manipulator and implement feed-forward control, which kind of justifies the quality of the obtained model. So if you're interested in this manipulator or in more details about how we actually develop those the models for constant curvature continuum robots, you can visit me later in Saloon 1 or 2 in the next session. And you can also play with a smaller brother of the bionic handling assistant, the Robotino, at the Festo booth in the exhibition here. Thank you very much.
Hi, I am Naoki Wakisaka from Osaka University. My presentation title is First and Reasonable Contact Force Computation in Fluid Dynamics based on momentum level penetration compensation. Our goal is to compute reasonable contact forces in fluid dynamics simulations with small computation cost. The conventional methods are classified into microscopic approaches and macroscopic approaches. The microscopic approaches track microscopic deformations in detail, which require too precise modeling. So the computation cost is usually large. In contrast, macroscopic approaches constrain contact point first, and then inversely compute contact forces. The cost is small, but contact forces often chatter, and the distribution of them tends to be unnatural. The macroscopic approach is preferable from the viewpoint of computation cost. It tries to constrain the contact points strictly, so that it causes chatterings. So we propose to relax the constraint as this quadratic programming. This term represents the restitution of microscopic deformation, while this term is for the force distribution. From the viewpoint of numerical property, this term is for momentum level penetration compensation, and this term works as Tikhonov regularization. So this method is numerically stable in time and space. We simulated a pendulum colliding to the ground by the microscopic and the proposed method. This table shows each interval to compute stably each calculation time and the corresponding normal contact forces. The result tells us that the proposed method stably provides this natural contact forces with a large interval. Thank you for listening.
All right, hello, my name is Matthew Travers. I'm going to be talking today about recursive dynamics and feedback linearizing control of serial chain manipulators. Start off with this video here, and basically the point is, depending on the form of your robot and what you're actually trying to accomplish, how you design and ultimately how you go and then implement your controllers can either make or break the performance of what it is you're actually trying to accomplish. Now in the last slide, the robot that we were looking at is the Carnegie Mellon modular snake robot. We've actually recently redesigned this robot to form what we now call the DARPA Series Elastic Snake robot. The main difference between these two is that we now have elastic elements in between the individual joints that compose the overall mechanism. And now adding these elastic elements, there's a number of advantages to doing that. The first is that we actually get mechanical compliance out of the system, and the other is that we can actually back out a torque measurement using Hooke's law at the individual joints. There's also a number of disadvantages. One being that you now have more uncertainty in your system. The other is that it's now more difficult to both model and control the system because you've effectively gone and added more degrees of freedom without adding any extra sort of actuation to go and control those additional degrees of freedom. And in this paper, what we address is the second of these points. And in particular, you saw in that first video, I coiled up a portion of the snake's body to effectively form a fixed base. And then I pop a number of models up into the air, and what I've done is I've gone and basically created a serial chain manipulator. And we've known for a long time, sort of in the robotics community, that computing the dynamics of these types of systems, there's enough structure in that we can actually go and leverage that structure to analytically compute exact expressions for the forward dynamics. And we've known this for a long time, but the novel contribution that we made in this work is we actually showed how you can take these analytic forms for your forward dynamics and use those to go and analytically calculate expressions for your nonlinear controllers. And in particular, in this paper, what we did is we show how you can derive a new set of coordinates that allows you to transform your original system and ultimately to go and derive your feedback linearizing controller. So this is a MIMO system. This is up to n joints this works. And you can do this all in closed form. And the cool sort of insight and what we're really sort of banking off and doing this in actual implementation is that this allows you to avoid having to go and numerically differentiate a measured output signal. Where when you're computing that actual differentiation, you might not just be computing the differential of your output, but also the high frequency noise associated with measuring it, which can give you arbitrarily poor performance of your controller, not based on the underlying physics of the system, but literally based on the underlying physics of the sensor that you're trying to help you actually learn something about the system. And that's sort of the main insight. And I'll be happy to answer any questions in the interactive session. Thank you.
I am Tokuji from Kyushu University, Japan. I'd like to talk about class planning constraint path object approximate with codec surfaces. Where do you grasp this object? Most persons grasp the constraint part of the object. However, previous class planners grasp the flat surfaces and do not sufficiently focus on the constraint part. Then we propose a grasp planner for constraint part and confirm that the graspability is more stable than at constrict path. In our method, objects are approximated by quadric surfaces, and one sheet paraboloid and a pair of episodes are extracted or other constraint path. Grasp postures are generated using the quadric surface parameter. And grasp stability is evaluated by using stress distribution. In case of the grasping of this object, previous planners evaluate the graspability using by the area of the contact regions only. Our method uses stress distribution and calculates the graspability accurately. In simulation, several objects are tested. Quadric surfaces and grasp postures and the values of grasp stabilities are shown in this slide. We confirm that grasping at constriction path is more stable than the others. Our method finds more grasping postures. We compare grasping a constraint shape and a complex shape, and we confirm that the grasping constraint paths are stable. Thank you.
Hello everyone, I'm Chi Zhang from Delft University of Technology. Today, I'm going to talk about how to make the robot grasp the unknown object quickly and stably based on the force balance optimization. When a robot comes before the target object, usually the first step to manipulate the target object is to grasp it. But the question for the robot is how to grasp it quickly and stably. Our successful grasp can be divided into grasp find and grasp execution. Here is the overview of the algorithm. From the and I means the grasp find. J is the grasp execution. Among them, force balance calculation is the key step, and it can be further divided into two sections. One is the force balance on XOY plan, and the other is the force balance on XOZ plan. On the XOY plan, the algorithm will search along the principal axis from the top to the bottom. On every grasp candidate configuration, the least square line-fitting method is used to fit out two straight lines according to the equation, and the angle between the two straight lines is worked out. And then the result of force balance calculation on the XOY plan is shown as a line chart. Find the best one and abstract the corresponding point cloud based on the used for further analysis. The difference between the average z-coordinate value of the two grasp sides is used to measure the grasp stability on XOZ plan. If the difference between the Z1 and Z2 is smaller than the threshold given by the grasping system, then it means that the grasp is stable, and otherwise the robot need to be driven to the second viewpoint. Here, the main plan is used to drive the robot. The main plan is shown as blue points in the image C and F. This slide shows how the robot to be driven to the second viewpoint according to the equation shown on the bottom. After the robot arrived at the second viewpoint, the algorithm will repeat above steps to work out a grasp. In order to examine the algorithm, several objects are used for simulation and experiment. These snapshots are the simulation result. The first column is the setup of the robot and the target object in the gazebo. The last column is the final grasp execution. The algorithm can quickly find the grasp point and grasp it stably. And this is the experiment. The left side is the experiment setup. The right is the experiment result. The final part of the paper is we compare our algorithm with other two popular unknown object grasping algorithms, and that is minimum bounding box and maximum curvature. Compared with other two algorithms, our algorithm is faster and stable. That's all. Thanks for your attention.
Good afternoon. My name is Tasuku Yamawaki from National Defense Academy. Today I'd like to talk about our initial efforts to achieve the robotic non-prehensive catching, as shown this figure. What is a non-prehensive catching? Non-prehensive catching is a robotic catching without being firmly grasped by robotic hand, as shown in this figure. One of the two fingers is inserted from below into the hole of the flying object, and then the fingers are moved closer together. The object is caged by the fingers. The object is confined within a bounded region. The proposed catching method has two advantages. The first is that there is less restriction of the size of an object as long as the object has holes or its shape is concave. The second is that accurate finger position is not required. The robotic hand should be moved to an appropriate region where caging is achieved, and direct contact between the object and the hand is not needed. The proposed catching method consists of two phases. The first phase, the non-prehensive catching phase. In this phase, a robotic hand confines a flying object within a bounding region. The second phase is a prehensive grasping phase. This phase is performed to immobilize the caged object by moving the fingers. We especially consider the partial cage catching of torus object as shown in this figure and propose a control strategy for this catching. To verify the proposed control strategy, we developed the robotic catching system. The robotic system consists of a high-speed vision system and robotic control system. By using the visual feedback system, the control strategy generates the arm motion online to catch the torus object. The strategy does not predict an object path and also can avoid a singular configuration. If you are interested in our research, please come to our booth, and thank you for your attention.
Hi everyone, my name is Boris Illing, and I'm going to present our work about changing pre-grasp strategies with increasing object location uncertainty. This work was a joint research with CMU and was supervised by Tamim Asfour at KIT and Nancy Pollard at CMU. First of all, why concentrate on human pre-grasp strategies? Well, reaching and grasping movements are, with various levels of uncertainty, are definitely part of our everyday life. We believe that robotic grasping can benefit from more insight into the way how humans handle uncertainty. For our human subject experiment, we used this rather unobtrusive experimental setup, mainly relying on HD video cameras. We conducted several grasping trials, putting one object at a time in front of the participant. The level of uncertainty was controlled through the actual object placement, where we would vary between the direct view case, peripheral view, and blind grasping. All the objects we selected for this experiment were typical kitchen items and tools, making sure everyone would be familiar with them. The objective was always to pick up the current object and move it to or use it at a target location. For our objective results, we analyzed about 1,100 grasps from 15 participants, and trying to categorize and explicitly name these all frequent pre-grasp strategies, we came up with this list of just 8 different strategies. The most used grasp in case of low uncertainty was a direct grasp approach. With this simple approach, people would move straight to the object and then grasp it. Whereas in case of high uncertainty, most participants would switch to a tapping approach using one or several taps to check the actual object location or orientation before finally grasping. Concentrating on these two strategies, we then evaluated them with our robot setup, consisting of this motorman robot and a shadowed dexterous hand. We compared the performance of these two strategies with varying amounts of uncertainty which was manually induced. To conclude, we could show that humans use only a very limited set of pre-grasp strategies, trying to reuse or combine them as often as possible. We could also show the main task parameters, such as grasp completion time, is significantly increases in case of high uncertainty. Even though the limited scope of our robot experiment, we could also already show that human observation can help when considering uncertainty. I'm looking forward to talk to you in the interactive session, and thank you very much.
Good afternoon. I would like to present work done at King's College London. My name is Caspar Althöfer, and I have collaborated on this work together with Agostino Stilli and Helge Würdemann. And it gives me great pleasure to introduce the shrinkable, stiffness controllable soft manipulator based on a bio-inspired antagonistic actuation principle. So effectively, you have seen the presentations earlier by Festi and the work by Howard Choset. What we're trying here is now to marry these two ideas. So we have a pneumatic system that is also actuated by tendons. And it's particularly fascinating in my opinion because it is just a simple approach, and we create a shrinkable, soft, bio-inspired, stiffness controllable system. Where do we get our inspiration from? You can see it here on the video. We have taken inspiration from the octopus, which is a system that has no bones inside. It's just tissue effectively and muscles that can move around. So we try to create something along those lines, and our structure is effectively made of fabric combined with an elastic membrane, elastic bladder inside, and tendons. And through the clever combination of these three elements, we can create this structure, which has a number of fantastic features. So first of all, it can be deployed. It can, the title is the wrong one there, sorry. So we can move it around, as you can see here. So here you can see tendon actuation, but now I'm coming to the deployability. So it can extend in longitudinal direction through pneumatic inflation. And obviously we can also reverse this process again, so we can deflate. And as you have seen already in the earlier video, so we can steer it, we can move it around, and can achieve nice motion into different directions. Having interest in medical robotics, we can insert it through a trocar port. It can then be moved inside a body, can be inflated, and then steered around to achieve positioning in that environment. I would like to thank partners in the StiffLab project, which was supporting this work. But what I haven't really spoken about, fantastic other feature, is stiffness controllability. So please come to our stand during the interactive session. And we also, I can show that, no, I can't show it. We also have a hands-on system there. So hopefully I'll see you there. Thank you very much.
All right, my name is Matt Travers again. I'm going to be presenting some work by Hugo Ponti. The name of this talk is going to be Guided Locomotion in 3D for Snake Robots based on Contact Force Optimization. The way that we normally think about controlling a robot on flat ground is we think about executing some gait. And we've designed a number of different gaits to give us a number of different kinds of locomotion. And this works very, very well on sort of flat grounds in the lab, or if I'm trying to avoid obstacles or something like that. But when I start to move to arbitrary terrains, it's no longer clear that A, this is even going to work, or B, if it does work, that it's even a good idea. So our approach in this paper is basically it's a simulation-based result right now because the hardware doesn't necessarily exist. We have spherical modules, and we have contact sensing on the outside of the modules. And the idea here is basically we're going to steal sort of concepts from manipulation. I've heard this called self-manipulation, if you want to think of it in that way. And the idea is basically I want to end up manipulating individual contact forces to produce some desired net overall force, acting or that my body is exerting on the actual environment. And how I actually can produce desired net forces is I'm just going to take sort of a vanilla quadratic programming optimization-based approach, where what I'm trying to minimize is the difference between some desired net force and my measured or my computed net force coming from my actual contacts. And then I also, inside of this P, which is my cost function, I also have to have this second term, which is for regularization, which basically says a large force over here can't cancel out a large force over here. And then we just basically stick this into a quadratic programming solution. And it works reasonably well, but what we actually noticed when we went and started to implement this is that you sort of get bad shapes of your overall robot. So what you actually have to do is go and sort of regularize the shape of your robot so that you don't sort of get into these degenerate configurations. And how we do this is we actually do a gain scheduling approach where we have two separate controllers. One is just executing a base gate, and then you can think of this second term coming from the contact force optimization as basically altering the base shape of the gate based on sort of trying to optimally push off the environment. And how we actually do the gain scheduling is we're going to use the absolute value of the underlying cost function itself to tell us when we're going to get a large advantage from pushing off the environment as opposed to just executing our base gate. And then this is just some short sort of preliminary simulation results. So we are actually building this hardware with the actual tactile sensors. But you can sort of see as the snake, the gray circles here are protrusions in the environment. And you can actually see the snake actually as it's moving, it's executing this base gate, trying to push off the obstacles to help itself better locomote. That's all I got. Thank you very much.
So good afternoon. My name is Jianwei Zhang from University of Hamburg, and the first author of this presentation is Junhu He. Unfortunately, he hasn't got his visa to come here, so I present this paper. So the title is Push Resistance in In-Hand Manipulations. So first, I introduce the motivation. That's a lot of dexterous manipulation in the daily environment are necessary. So usually we need more than just two finger hands. So this high degree of freedom anthropomorphic robot hand, like Robonaut, DLR, HIT, and the shadow hand. But until now, there's still a lot of robustness problem, dexterous problem, and haptic-based manipulation still unsolved. So for the real applications. So in this work, we are concentrating on the touch force, which can overcome the geometrical informations like human using active touch. And we consider also the interaction with a black box is perceived from trial and error. And it's on the haptic feedback. Here we have the finger and object. And in this paper, we devised two models. First is a single finger push model. And the second is a spatial multi-finger push model. And in the paper, this is a detailed mathematical description. And here, this paper for validation, this concept we tested with the shadow hand. And the shadow hand is equipped also with the biotech syntax sensors with each finger about 9 measure points. And we test with bottles and also foam. And so this is the first experiment with about the push direction, have two support fingers and one push fingers. And this is a model about the support fingers and the push directions are modeled. So this shows some of the data and also the maximum point shape and convex data. And this second experiment about push distance and the press angle, and I show you a short video. That's so in this video we show some of the in-hand manipulation we have done with this pipetting task. We show that this kind of modeling, also handling with different objects, is really necessary, and more experiments will be shown in the interactive session. Thank you very much.
Hello, my name is Roberto. I'm working with Oliver Brock at the TU Berlin, and today I'm going to present a perceptual skill to support the manipulation with articulated objects. Articulated objects are everywhere, and their kinematic structure, their structure of rigid parts and connecting joints is very important because it's connected to their functionality and because it helps us to know how to actuate them. Robots that want to manipulate in human environments need a way to perceive these structures and to understand interactions with articulated objects. In the next videos, you will see the input to our algorithm, which is the RGBD stream of a Kinect sensor, which I show the color images here, and superimpose the results of our algorithm, which is the kinematic structure perceived through interactions. Our algorithm perceives or infers the type of joint, which is shown in red for the joints that are revolute and green for prismatic joints. And it also estimates the parameters of the joint, like the joint axis. It estimates the joint state as well. Our algorithm is capable of self-assessing its own uncertainty about the estimates, and this is shown with these translucent cones in the videos. The algorithm continuously integrates new information as soon as it's perceived. In this way, it can correct wrong initial measurements like these revolute joints that are initially perceived as prismatic because small rotations can be perceived as translations at the beginning. I also show that the algorithm works fine in clear environments, but also in clutter environments or environments with distracting texture. The skill is robust and versatile. It can perceive the kinematic structure of semi-rigid objects like my neck, of articulated objects actuated sequentially, of coupled joints, and of kinematic change like the Puma robot. The novelty of the algorithm is in the fact that all these estimates that are obtained for previously unseen objects and without using markers, all these estimates are available during the interaction. And this is very important because we can use these estimates to control the motion of the robot and the interaction. Like in this example where the robot is using the online algorithm to open the cupboard door to a certain configuration and then close it again. So I hope I triggered your interest in this topic, and I would be very happy to talk to you more in detail and explain you how we do this using recursive estimation during the interactive poster session. Thank you very much.
Hi, so I'm Martin Levin from Georgia Tech, and I'm going to present you some work on using environment objects as tools to unconventionally open some doors. And this work was done in collaboration with my former advisor, Mike Stearman, who unfortunately passed away a couple months ago. So if you look at robotic systems today, and we have seen many at this conference, then they can assert an immense amount of force on the environment. However much force they can assert on the environment, it's always going to be somewhat limited. And that is similar to us humans. So right, we have like some human can assert a little more force than another, but we are all limited in the amount of force that we can assert on the environment. So if we are faced with an object that we really, really want to move, but we can't do it within our force constraints, then we tend to use objects in our environment to be able to increase the force that we are applying to that object. And in this paper, we are proposing that robots should do the same thing. And in particular, we are studying the problem of opening a door that is either locked or jammed. And we're interested in algorithms that allow the robot to open these doors by using objects in the environment. And particularly to either build itself like a lever-like structure, or to even maybe build itself like a battering ram and ram the door with something to then eventually unlock the door. And while you think this might be like a very well-defined problem, where we know all the physics that are relevant for this problem, we just take the equations for the mechanical advantage that is provided to us by lever, or use the momentum equations to decide on how much we have to hit the door with. In practice, this is a very difficult problem, right? Because the robot has to decide on discrete choices like which object to use for what task, and on continuous choices like where exactly to place the lever on the door. So on this work, we are proposing to, instead of making these kind of choices sequentially, like first deciding an object and then deciding on where to place it,
to first forward propagate the physical constraints that are imposed upon us from the task as much as we can to reduce the overall search space. So basically what we're doing is we're building up a smaller space that is guaranteeing us to contain the solution, but that we can more efficiently search. And then we just sample solutions within that space until we find a solution that satisfies all our constraints. And the algorithm comes up with interesting results, like in the top result, it decided to move the card closer to the wall to then use it as a fulcrum to open up the door. Or in the bottom example, the algorithm decided to place some books on a card to then ram that card into the door. So I'm sure you have some questions, and I will gladly talk with you about those at the interactive session. Thanks.
Hello, my name is Christopher Palitz. I'm also with the Schunk company, and I just wanted to give you a few information what we do at Schunk. A few of you might already know us. We have lightweight arms and robotic hands, but Schunk is a lot more than that. We're a German-based company that does all sorts of automated components for automation. You see a wide variety from grippers over tool holders, rotary units, stationary units, chucks, linear technologies. But since most of you are robotics guys, I would like to give you a few more informations on our lightweight arms and products, how all started. Actually, we're working in the field of robotics already since 1983, where we started with a sort of first industrial gripper. This has evolved over the time up to a 5-finger hand, fully actuated, which you can see down in our booth, which I hope you'll visit. Parallel to the grippers, we've also been developing lightweight arms, also starting already in 1993 with a modular approach. The goal always being absolutely implementing all the necessary technology into the joint itself, which then makes it easier to integrate into all kind of mobile applications. So the focus of our products are definitely mobile and sort of battery-based applications. We have a good weight to torque ratio, sort of starting at around 14 kilograms with a 6 kilogram payload, reaching up to 15 kilogram with a 15 kilogram payload with 25 kilo of its own weight. We always have integrated cabling. We have the integrated motor drives and controllers, and also integrated tool changer, which allows us to attach all sorts of different end effectors. Of course, these are more sophisticated end effectors, which you can also see down at our booth. I'd be happy if I could talk to a few people with a few people there. We have robust industrial grippers, multi-finger grippers. We have humanoid hands, but we also have a whole range of accessories from force torque sensors over simple gripper, robot controllers, and tool changers, which adapt seamlessly into our robot arms. Last but not least, I'd like to do a little bit of advertising besides our hardware for our Schunk Expert Days. They take place every February, every year, where we invite speakers and participants from all over the world to discuss the service robot industry. The focus is much more on applied solutions and the business, and not so much on, say, technologies being developed. So if you have further questions about joining the Schunk Expert Days, please also come and talk to me at our booth downstairs. Thank you very much for your attention.